So today's topic, we are going to talk about what is quantum computing. Quantum computing demystified, impacts, timelines, and how to get quantum safe. And let us start. So today's session will basically talk about some of the core ideas about quantum computers, like what are the different topics we should be aware of from a security perspective. We should know the some basics of quantum computing. Then we'll go directly towards the real progress that is happening in hardware and error correction in quantum computing. We'll discuss about them, and also discuss about the US NIST, their standardization effort and what they have already standards are released, and also UK's National Quantum Strategy already released. So we'll talk about them, and then we'll explore the source and Grover's algorithms and why they are impacting today's cryptography and what we can do using the existing standards, existing solutions, and what is usually advisable or recommended by NIST and different national agencies, including UK. And some trials are already there in UK. So let us start. So let us talk about some of the basics, basically how it works without going into the lot of mathematics. But still we need to understand a little bit about the some of the representation. So when you are talking about quantum computing, there is a term qubit. So basically when you are talking about in classical computing, digital electronics or digital computing, we are talking about bits, that is binary. There are mainly two states are there when we are talking about classical computing, that is logic 0 and logic 1. So that's the binary Boolean logic. In case of quantum computing, similar analogy we can make, and it is quantum bit, that's the term qubit. So it can have basically uh, uh, two different states, that is logic 0 and logic 1. But because we are talking about quantum uh, elements, quantum computing, so quantum mechanics, there is specific properties there. It's called quantum superposition. So that's exactly what makes this field of quantum computing. So there are another specific description is there, which also makes that entanglement. But superposition is one of the major element which makes it so much interesting. What it means basically is that instead of definite at a particular level or particular state like 0 or 1, it can be at 0 or 1, and it can be at both of them at once. So it can, like the quantum state can be a complete or total superposition or a combination of different probabilities together. So that is the like a main element which makes it quite interesting. So we'll talk a little bit about that just after this. And there is another property, as I said, entanglement. Quantum entanglement is basically another interesting property where uh, two different particles or two different qubits, multiple qubits more specifically, there is a possibility they can correlate with one another. So that means there is the property of entanglement states that when there is like different entities like a physical particles like a photon or electrons, when they are entanglement in a situation when they are correlating, so we cannot describe any particular one entity separately. We have to, when you are describing uh, their properties, we need to describe the whole system together. Even if they are separated quite far away, like physical distance may be quite far away, but still, if they are entangled, then we have to define or we have to describe the whole thing together, and that's the main property. So that's the entanglement issue, and that is quite useful also in some of the situations. Now, another interesting thing we need to understand is basically for the measurement. So, when we are measuring, so first of all, before going to measurement, there is this sphere is given here. This is basically called a block sphere. Now, this is to represent a quantum state. So the surface of the, I mean, every point in this sphere or the surface of the sphere, we can uh, use every point to represent a qubit. So there are other ways to represent qubit also. So this cat representation of this is, for example, this is the red line. This one point on the surface, it is pointing to only one point on the surface. So this psi cat, this is the representation of one quantum state, and it can be represented by two angles, that is theta and phi, in this particular representation. And that we have a specific equation or formula for that, which will uniquely describe that quantum state at this particular location or particular point on this block sphere. Now, this is visually nice to see, and also, so another thing that when we say about this surface or all the points on this surface, we are basically talking about pure quantum states. There are different mixed states are possible. So that is like if there are entangled states, or there are some other operations are done on them. So there are some mixed states are possible. So those points will become inside the sphere. And another interesting part, or why we can see this block sphere in many places, is that uh, when you're talking about quantum logic gates or any quantum computing or any operation done on any quantum state. So basically, we just need to rotate the sphere. So the point will like move somewhere else, and that's the new updated quantum state. So that's the main purpose of this, or why this is so prevalent. There are, of course, other ways to represent quantum states are there, like more mathematical forms are there, and they are also useful. But this is nice to see visually. That's why I'm showing this. Now, yeah, so I was talking about the measurement part. So there is this important aspect from quantum computing we need to know, that is, whenever we measure, it basically uh, collapses the wave function. So that means that when we are talking about quantum state, as I said, for qubit specifically, this is a binary two states possibilities are there. I mean, they can be at any state or both state at the same time. But whenever, as soon as we measure, that will reduce the all possibilities, and will have a single particular probability or single particular observation, or a single state we can measure, and all other probabilities go to zero. So that will give us something called classical bit. So that is a fixed bit. So we can observe, when you observe, it becomes basically gives a classical bit. So usually whenever we are talking about any quantum operation or quantum logical operations, so we don't measure. We usually, so quantum logical gates, they usually operate on the quantum state itself, so that they are basically reversible quantum operations. So I'm not going into much detail into those directions, but the idea is that we don't measure, we just operate on the quantum states, and the result will remain quantum state. So unless it is required, so of course, if it is required, then we can measure, and it will collapse the function, we will get a single classical bit, means single observation. So that also actually defined what is the main principle, or how different types of logic, quantum logical operations they work. Or when you're talking about quantum algorithms, so all the research, all the current state, like whatever is proposed till now, whatever is currently available, we'll talk about that in more detail later. But what is the basic underlying principle? So underlying principle is that uh, so so there is this line you can see later that I have written, that quantum does not mean faster for everything. It is targeted, it basically has targeted speed up for specific problems. So if we have a we have quantum computers in UK also. So when you have quantum computer or quantum algorithm is there, it doesn't mean that it will make every like a classical algorithm or classical operations faster. So that is not the case. So the of course we need to understand one thing, that it is possible, it is not impossible, it is possible to implement or perform all current like logical classical algorithms using quantum computers, quantum logical gates. That is possible, that is absolutely possible. But the question should be, is it useful, or is it efficient enough? That means, is it faster than the classical all algorithms? Is it cheaper, or is it more accurate? So those things, unless it is there, then there is no benefit, or there is no advantage. The term is quantum advantage. So unless there is quantum advantage is there, then there is no point. So that's what I was talking about here, that for the quantum algorithms, how they propose, or how we work, or whenever you see any kind of proposal, they basically work with some kind of interference. So when you're talking about wave functions, basically, so the algorithms or the operations, quantum logical operations, are operated on the quantum states in such a way that all the correct answers, so we can have correct answers, we can have wrong answers, incorrect answers also, so at the same time. So we need to interfere constructively to the correct answers, so that their amplitudes get higher and higher, and for the wrong answers or incorrect answers, we need to do destructive interference, so that their amplitudes go lower towards zero. So that's the part, that we need to engineer interference in such a way so that we amplify the correct answer. So why do that? Because that observation that I mentioned, that whenever we make any measurement or observation, actual observation, we only get one information, or one bit, or one specific result out of it. We don't get we should not want to get the wrong answer also. If that will happen, what will happen is that the actual observation can be the probability, if it is high enough, then we can get some possible probability of wrong answers also. So always the algorithms try to have in such a way that the correct answers are amplitude are amplified enough, so that when you make the final observation or measurement, we only get the correct answer. So this is till now only observed in certain scenarios, certain applications, and in those specific problems only there is a speed up, at least till now, that is observed, and that's where quantum computers are going to make any like a better than the current classical computers. Right. So in our case, from security point of view or cyber security point of view, there are algorithms are there that matter, right? So as I just mentioned that previously I mentioned about this SOR algorithm. So there are mainly two algorithms are there which we need to be aware about. So SOR's algorithm and Grover's algorithm. So SOR's algorithm, when the SOR proposed that, so it is basically, it can factor the integer. So it can factor integer to make like we can get the prime numbers, and also solve the discrete logs quite fast. So quite fast means it is basically exponential speed up it can give. That's the main point of headache from asymmetric cryptography point of view. So that means it threats. So when you're talking about factor integers, that means it is threatening the RSA. When you're talking about discrete logs problem, so this is ECC, even elliptic curve. So ECC and Diffie-Hellman. So we can that's a problem. So that's one of the reasons why NIST they started standardization for asymmetric cryptography, and already standardized those standards are released already. Now the second algorithm is Grover's algorithm, which basically provides quadratic speedup for brute force. So this is like unstructured search. If you want to do brute force, for example, symmetric key block ciphers, so or hash functions. So those things, so what will happen is that when you apply Grover's algorithm, it will provide you quadratic speed up. So it will basically half the symmetric key link. So if we have like AES 120 bit, effectively, like at least from theoretical point of view, it gives 64 bit the effective strength. And so that is why the recommendation is that we need to go for 256 bit or higher, so that effectively we can get at least 120 bit. So that is strong enough even to the security point of view. So that's the Grover's. But try to we can identify that this source algorithm, it gives exponential speed up, whereas Grover's algorithm only gives quadratic speed up. So this point is quite important, you need to understand. And so main practical takeaway is basically we need to migrate the public cryptographical the solutions as soon as possible, instead of waiting for the realistic high computing power quantum computers to arise. Instead of doing that, we need to try to migrate as soon as possible and use longer symmetric keys for the block ciphers like AES 256. So state of play currently in 2026. So for hardware, there are steady advances we can see in literature and everywhere. So there are claims of quantum advantage. So if you remember, we just talked about quantum advantage. So that means, is it faster? Is it cheaper? Is it giving me more accurate results compared to classical computing? So then only it is quantum advantage. So currently it is reported for boson sampling, if you know. So basically it's a Gaussian boson sampling, very specific type of sampling for a specific probability distribution, for mainly for photonic quantum computing. It is shown that it is claims are there and it is shown there. And that is like the sign that we are going towards the direction where more and more feasible quantum computers in terms of hardware implementation, actual hardware, we can reach there. So that is why UK National Quantum Strategy was released in 2023, started already from 2024. It's a 10-year plan. So its plan is basically to have a investment of 2.5 billion till 2033. The UK is planning to be like top 3 in the world. And already, if you see, there is a quantum cryptographic national laboratory is there, UK. So they are already around, I think, 7 quantum computing test beds are already there or under installation, under deployment. So that those test beds are already started. Their plans, they were released in 2023. So it's already that we are in the plan already. So roadmap. So from the industry point of view also, there are reports from different companies that they're targeting this advantage. As I said, quantum advantage specific term. So basically from a real application or any specific application point of view, that there is advantage. So you have to go there. So that's the target. So in I think this year only, yeah, Google research. So they already showed that quantum error correction. That's the part where, so this is, so let me explain a little bit about quantum error correction. So when we have physical quantum qubits, or when we want to implement any quantum logic gates, so what happens is that due to physical environmental impact, there is something called decoherence. So the quantum state becomes unrecognizable, or we cannot make use of it after some time. So that's the problem. So to solve that, there are some error correction algorithms are proposed, quantum error correction, different types of codes are proposed. And this is one thing they have proposed from Google. So dynamic surface codes. So basically the surface codes are usually static, but it is dynamic. So the idea is that for their particular processor, I think it's called Willow. So they have proposed it. So they have shown that it's published that they are able to get some kind of advantage for specific applications. So that's the part they have shown. So IBM also have released something called Nighthawk processor. So they have some their own roadmap. So different companies they are proposing, but more or less they are targeting similar roadmap. So yeah, so there are other companies also, and they are targeting also fault tolerance towards the late of like around 2029 or something. So that's the current stage in this year. So we can see. Yes. So regarding quantum safe computing, so as I mentioned that already NIST has standardized. So there are mainly three standards already is there. So one is the FIPS. So I think here I have mentioned FIPS 203, 204 and 205. They are finalized 2024. So 203 is this one, MLChem. This is basically from a implementation called Kyber. This is the key encapsulation mechanism. And the remaining two are basically the signature, MLDSA and SLH So this is from Dilithium and Sphinx Plus. So another one is from Falcon. It's already is there. I mean, almost published. I think this year it will be published. 206, FIPS 206. And another key encapsulation mechanism also standardized last year from HQS something. So yeah, so the recommendation is that we need to have a plan for migration. So whenever we are talking about any kind of high value long lived data, so there is this problem of store now decrypt later. So SNDL. So that's the problem that if you store now and if you want to have a high enough high capacity powerful quantum computers towards the end of this decade, then you can basically break all the asymmetric cryptography RSA and you can gather the secrets. So if there is any possibility that we have any long-lived data, it will be valid for more than, let's say, 10 to 15 years or even more than that, 20 years. And if the value of the data is high, so we can prioritize those data for this kind of migration as soon as possible, where we can utilize the already standards are there, so we can just try to have them. And instead of going abruptly from existing asymmetric cryptographic to the quantum PQC standards, there is a suggestion is always to go for hybrid. So where we have the existing and PQC together, and then we can change to the PQC completely. So that's the main suggestion nowadays from even UK and also NIST US. They suggested that, and so that's the main crypto agility part, that we need to have a crypto agility. We can have all these algorithms we can support, and we can map to the existing FIPS standards. So in terms of quantum protocols and networks, so QKD is one well-known algorithms, quantum key distribution. So I was just trying to say that QKD is a one such protocol, which is where we basically transfer the keys, and it uses quantum states, but the observation is always made in classical observation, classical bits. So there is a trial already going on in London. At least two trials are there between different data centers, and British Telecom is and other companies are doing that. And we can also have a combination of PQC with QKD, so that will also make sure that we have a quantum network, and in future we can go for quantum internet. So this is my last slide basically. So what we can gather from this all the discussion, there are mainly few research direction I would like to point out. So in theory, all this PQC implementation and everything is secure, that is fine. But in reality, when you talk about the implementation, we'll see that there are problems of side channels and fault attacks are there. So we need to be careful. There are different implementations and papers are already released, which shows the vulnerability of implementation. So That is one way of looking at from the research point of view. And hybrid protocol, as I just mentioned, that there are some works are already going on. And when you're talking about this quantum advantage, we also need to be careful which is more relevant from security point of view. What is actually, so instead of physical qubit, what is logical qubit point of view? There are differences, as I said, quantum error correction point of view. So what is the main security relevant workloads or benchmarks are there? So how to do that kind of testing, how to do that work. So that is another main impactful research direction. These are some references that I have used. Thank you.